Welcome back, everybody. First of all, I want to sorry with all the students on YouTube because I've just noticed that I wrongly set my lesson number 4 on Monday instead of today. I don't know why. Of course, it's my fault. However, I hope that you can still follow it, and if this is not the case, for sure you will be able to see the recording at least. So the last time we were discussing about. Let me go back to external monitor. Last time we were discussing about the basics of the C programming language. We saw how to declare a variable. Well, first of all, we saw what is a variable. We understood that a variable is equivalent with the type and the name. We saw how to declare it. And we understand that we are able to assign that variable by providing an expression which is evaluated, and the value of the expression is set into the variable. Besides the arithmetic part, we can also define Boolean expressions. So the algebraic relation are the standard one, of course. So we have the equality, the diversity relation, which is exclamation mark equal. And we have the majority relation, and so the derivatives. But besides this part, we have also Boolean operators, just like the logical conjunction, which can be used by specifying to subsequent ampersand. And we also have the exclusive disjunction, non-exclusive disjunction, which is defined by 2, which is, how can I say, usable by providing 2 pipelines. And moreover, we also have logic negation, which is specified by using the single exclamation mark. Now, how can we use all these operators since we haven't any Boolean type? Well, the point is the Boolean type is not really necessary in the C programming language, because you can use any natural value, or any value actually, any value to represent Boolean values. And the idea is that the 0 represents the Boolean value false, while any other value different from 0 will represent the Boolean value true. Okay? So if you have an integer value and you may interpret it just like a Boolean value, that integer, if the integer value is 0, then the corresponding Boolean value will be false. Otherwise, you end up playing in a true Boolean value. Now, because of this, of course, you can easily build up a Boolean expression, just the one you can see here. I want to recall you that D and I are basically meant to be integer values. B is defined as the char values. S is, I don't know actually. But however, you can ask whether is it false that I is greater or equal than 3, and at the same time D minus 2 is equal to minus 1, and the value contained in the variable b is different from 0. And this is the first part of the Boolean expression. Then, by applying two pipelines, subsequent pipelines, you are using non-exclusive negation, non-exclusive disjunction. So basically, you are saying whether the first part of the expression is true, or the second part of the expression is true, or both of them are true, then the Boolean expression itself is true. Okay? Well, to be honest, from 1999, we also have a Boolean type in C, in the definition of C. So it's a standard type, but actually, I mean, no one uses it. So it may be the case that some compilers don't even implement it. So the best thing to do is to go straight forward to the plain fake implementation of the Boolean, well, fake. I mean, the naive implementation of the Boolean type, so the one made up by using integer values, and I mean, it's much easier to guarantee that your program will compile. So once we have defined what is an instruction, more or less, what is an assignment, variable definition, and so on and so forth, we may want, for some reason, try to collect a sequence of instruction, because from a logical point of view, they behave to the very same high-level operation. And to do it, the syntax of the C programming language let us to use braces. Okay, so the braces can be used in some sense to define a block of instruction. Well, not in some sense. They really allow us to define block of instruction, and the syntax is the one you can see on the slides. So open brace, sequence of instruction, close brace. Now, inside a block, you can do everything basically we saw until now. So, for instance, you can define a variable, declare a variable. Okay, but what is really important to remember is that the variable defined inside the block ends to exist once that block is ended, is concluded. So to say, if you have a look at the slide right now, you see that we are declaring the variable h inside the block, and so we can use it. But as soon as we end the block, the variable h doesn't exist anymore. And this, how can I say, this boundary for the existence of the variable has a specific name, which is named scope. So the scope of the variable is the, let's say, location in which a variable can be used or seen by the program itself. Of course, it could be the case that just before the block I have defined another variable named h. Okay, so it could be the case that by using the block system I'm able to define twice, well, to define two variables whose name is the same. But of course they are different variables. Okay. Again, just to make an example, let's assume that just before this block we have defined the variable h and assigned it to 2. Entering into the block, the variable h assigned to 2 still exists, but once I define a new variable named h again, the previous variable in some sense is hidden from the new one. So I'm not able anymore to refer to it. Still exists, but since I've, in some sense, overwritten its name, I'm not able to use it anymore. Until when? Until the end of the block. So once the block is concluded, I'm still able to see the previous variable, I'm still able to read it and to write it. And the value contained in that variable, of course, will be the same we last inserted. So due to the last assignment. Okay. So this is it. Now, another, let's say, rather important thing to do with the program is to let your user what you are doing. And this is done by printing into the standard output usually. So if you are computing something, you probably want to let the software user what's going on and what's the result of the computation. And to do it, we have to print the result. So to print the result, we have to use the instruction printf. I mean, it's not really an instruction, but you will see, I mean, by the end of the lesson, why I'm saying that it's not really an instruction in the strict sense, let's say. This, let's say, instruction as the syntax you can see here. So the idea is that you write printf, open parentheses, quotation mark, then you write something, you close the quotation mark, you close the parentheses, and that's it. And you are printing what is in between the quotation mark on the standard output. Now, of course, if you are exclusively allowed to print strings, so what is in the middle of quotation mark, you end up in producing almost useless program, because usually, well, this is not really true, but I mean almost. Let's say it could be quite tough here to provide a meaningful result if this was the case. However, as you can see from the second line in the slides, we are also able to print in the standard output the content of variables. And this is done by using what we may call placeholders, let's say. So the idea is that in the string we want to print that is basically what is contained, as already said, is contained by the quotation mark. I'm saying, look, inside this string I want to place the content of a variable. And this is done by using the, let's say, special character percentage. So the special character percentage in the C programming language is meant to say, look, I'm going to print the content of a variable. And the next character basically is telling to the compiler how the variable must be interpreted. We saw that the variable is basically a container, and we understood that a container in the memory, of course, and we understood the memory into a computer program is organized as a sequence of bits. So, of course, any sequence of bits can be interpreted as a natural number, a character, a floating point number, and so on and so forth. So, we need to tell to the compiler how to interpret the content of the variable we want to print. And to do it, we have to specify something after the percentage character. Here we are saying that the content of the variable must be printed as a decimal number. That's why we are reporting the D. Okay? Of course, you may think a situation in which, for instance, you want to print the hexadecimal representation of that integer number. And in that case, you will use a different letter. Okay? Or, I don't know, since we understood that also characters are internally represented as a number, if you remember, we talked about the ASCII coding. It may be the case that the value which is contained by the variable I should be represented as a character. So in that case, we will use a different letter to represent it inside the string. Okay? So here we have three placeholders in our string. All of them should be decimal number. And after the string in the printf instruction, we need to provide 3 different expressions, let's say. I mean, up to now I just talk about the content of variable, but I mean they could be also expressions. So, for instance, the second, I mean, value you provide to the instruction printf could be 2 multiply I, for instance, just to let you know. However, the point is that since we have 3 placeholders on the string, we must provide for sure 3 different values after the string itself. And so, as you can see from the slide, here we are providing twice the same variable. I mean, this is not really useful. It's just to show you that you can do it. What about the floating point number? So we understood that %d give us the chance to print a decimal number, but what about floating point numbers? Well, for floating point numbers, so number having a dot, okay, you can use %f. By writing %f, you are saying that you want to print in standard output the floating point representation of the variables. Okay? And what about characters? Well, if you can have a look to the last 2 lines of our slides, I'm sorry for the people on the first line, first row of the class. However, here we are declaring a variable, a character variable C, and at the same time assigning it to capital Y. Please notice that we are using apostrophes instead of quotation marks to define the character. This is quite important, and we will see why by the end of the lesson. So once we have defined the character variable C, we want to print the character in the standard output, and to do it we use %C, meaning the value of the string. How can we do it? Well, we can do it by using the / escape sequence. We may have a tabulation issue, and this can be solved by using the /T. We may want to represent, since we understood that all the escape sequence start by using a /, what if we want to represent the / itself inside our string? Well, to represent it, we simply have to use another escape sequence, which is /, which will be printed as a single / in our standard output. Of course, we have also a problem with the quotation character, quotation mark. Why? Because we understood that to represent a string, we have to start it with a quotation mark and we have to end it with a quotation mark. But what if you want to represent inside our string the quotation mark? If I place a quotation mark by its own, I'm saying, look, this is the end of the string I want to represent. So we need a way to represent the quotation mark inside the string, and this is done by the escape sequence / quotation mark. Quotation chart. Okay, this is more or less, well, /A produce a sound just like an error sound. For instance, if you try to open your terminal and entering something in your shell, and you keep pressing the backspace character, which is the one that deletes the last character, eventually you will end up at the beginning of the prompt, let's say. Okay? If you try to press the / again, you end up in an error, which is a warning telling you, look, you are trying to delete something which is not present. There's nothing more on your prompt to be deleted. Okay? And that's one sound is an alert, and you can produce it in your program by using \a. And finally, and most important, there is a really important character, which is the string terminator. What is the string terminator? Well, the string terminator is a character which tells our compiler that the string is dealing with ends there. Okay? This character is automatically added to the string once you use the quotation character, let's say, to define the string. So you don't need to add it to the string you are defining. But you will see, if you try to define the string by appending a sequence of characters, for sure you need to add the string terminator, otherwise the compiler doesn't know that the string ends and keep writing things on the standard output by reading the memory just after the variable you start using it. And that's why it's important to distinguish the apostrophes from the quotation mark. Because by defining a string with a quotation mark, you are automatically appending the string terminator to the string itself, while by using the apostrophes, you are talking about one single character and the string terminator is now appended to it. Okay? Great. We will see how to build up a string starting from a sequence of characters. I mean, not this type, but for sure on Monday. Now, okay, this is just a set of examples. In the first line, we are printing in standard output a string which contains two quotation marks, quotation character. In the second line, by using one single instruction on one single line, we are printing in the standard output two lines. The first one contains the word "this does," and the second line contains the words "but this not." Okay, but it's important to understand that the printf function does not end the string by carriage return. So if you try to print by in your program a string, you are not going to the next line after the string. So if you want to go to the next string, you have to append to this second instruction the \escape \n escape sequence. Okay. The third line is going to produce a sound. The second last line is going to write everything in the string but the last R, and this is due to the fact that \b means backspace character. So I'm writing everything, but as soon as I read this character, I end up in deleting the previous one. Is it clear? And what about the last line? I don't know if you can see in the class the last line, but okay, just let me check whether okay. So not really okay, but let me move this stuff here. No. Here. So the last line, for instance, is trying to print a string, which is a weird string. And the motivation is that the string itself contains the string terminator. So it's not at the end of the string, added by default by the quotation mark syntax, but we are providing it in the middle of the string. Okay, so we are trying to write something like this line, string terminator ends before the real end. So if we compile this line, so if we write a program containing this line and we try to execute it, we end up in seeing on the standard output this line E. And everything after the termination, the string terminator is not present, is not displayed. And the reason is that the string terminator and the string just before the real end of the string. Okay? So in some sense, inside our program, the string is present until the end, so word. But if you try to print it, the printf command, in some sense, stop to print the string once it discovers the string terminator. Okay? Is it clear? Great. So now we saw how to declare a variable, we saw how to assign a variable, we saw blocks, we saw how to print a standard output. We are missing something else to write any possible program, and in particular we are missing loop statement and something else we will see later on. But what are loop statements? Loop statements are a syntactic way to keep repeating the same block of code many times. And the C programming language provides two kinds of loop statement. The first one is while do, and the second one, the for loop. So the while do statement works more or less in this way. You write while, you need to provide a Boolean condition, and then you have the block of instruction you want to execute. Okay? Now, the Boolean condition, so until the Boolean condition is true, you keep repeating the block. Once the Boolean condition became false, you exit from the while loop and you execute the next instruction. So the instruction which comes next to the block. Okay, in this case, for instance, we don't have any instruction, the program ends up there. Let's have an example. This is the example. So we are declaring the variable I, assigning it at the same time to 0, and we are saying while the content of the variable I is different from 4, keep repeating this block of instructions. So the first thing we do in the first iteration of the while loop is to print into the standard output here I is equal to the content of the variable I. Of course, in the first iteration of the while loop, we are printing here I is equal to 0 because we assign the variable I to 0. Okay. Then the next instruction is to, let's say, increase I, and here we are seeing a kind of shortcut to the assignment of the I variable. By I mean something like I equal to I plus 1. Okay? This is a shortcut. Instead of writing I equal I plus 1, I'm simply writing I plus plus. That's all. So once this instruction is executed, I conclude my block, and so I must go again to the while statement and test again whether the condition is true or not. Now, after the instruction of the last instruction of the block, I contain the value 1. So again, Is it true that the content of the variable I is different from 4? Yes. So again, I'm executing the block. This time, the printf instruction is printing here I is equal to 1. And again, I'm increasing I by 1. So on and so forward, until the end of the fourth execution of the block, in which I'm basically increasing I from 3 to 4. Now I is equal to 4, yes. I'm taking the negation because of the exclamation mark, and so true. Sorry, false. The negation because of the exclamation mark, so false. Is it true that 4 is different from 4? I is different from 4? No. So the while loop stop the execution of the block and skip to the next instruction. And that's it. Okay? Yeah.
At the end of the loop, I is 0.
At the end of the loop, I is equal to 4. Because as you can see here, I'm not defining any new variable inside the block.
So
I'm changing the value of the variable I.
after the loop, I, because I is changed inside the block.
Yeah. But you are, I mean, this, don't be confused. The variable I inside the block is the same variable outside the block. So it's that one. Okay. We saw that inside the block I can define a new variable whose name is the same as the variable outside the block, but this is not the case. So when I write I mean this variable. Okay? And the result of changing it inside the block is preserved also outside the block. So this also holds if we weren't dealing with the while. So if I remove the while statement and I simply define the variable I and I define a block, the result of execution of all this instruction would be to have I equal to 1. Okay? So no matter the fact that you are dealing with a block, the result of the operation will always affect the variable at the top level, let's say. But this of course holds exclusively when you are not defining a new variable whose name is the same of the variable outside the block, which is this case. Okay, so this is more or less how the while do loop works. What about the for statement? Well, the for statement again is a statement meant to allow you to repeat a block many times, but it works in a, different way. Well, it works exactly as the while loop, but it gives you the chance to avoid to take care of increasing a variable every time you end the block. We saw in the previous example that we had at the end of the block take care of I to increase it. Okay, so in some sense we have during the writing of the program we have to remember that we need to change something to change the evaluation of the condition in the while loop. The for loop provides a syntax way to force you in some sense to change something. And this is done in this way. We have this syntax. So the first, we have for, we have to open parentheses. The first, let's say, sub-instruction, if you want, the first part of the stuff inside the parentheses is the initialization code. So this code should be executed just before the first execution of the block. Okay? Then we have a loop condition which is totally identical to the one we saw on the while loop. So as soon as that as soon as that loop condition is false, the for loop stops its execution. Okay, but while the loop condition is true, the for loop keeps repeating the block, and so it's totally identical to the while loop condition. This condition, and the third part of the for loop statement block, let's say, is the updating code. So it's the code meant to update the status of the let's say condition we want to deal with. And as you can see here, in some sense you are forced to place your updates here instead of remembering that you need to update something just we did on the while loop condition. Okay, so going back to our example in which we want to declare a variable starting from assigning to 0 and keep printing the content of that variable until it becomes 4. We may use the code you can see in the last part of the slides. So we can write for int j equal to 0. So we are, for the initialization part, we are declaring a new variable, which is j, and the variable exists exclusively exclusively for the scope of the for loop condition. Okay? So we declare a variable j, we assign the variable to 0, then while j is smaller than I, if you remember at the end of the previous loop I was equal to 4, so basically this is just like say while j is smaller than 4, keep repeating the blocks, and at the end of the execution of each block you have to increase j by 1. So these 3 lines are from the functional point of view, so from the point of view of the result, let's say, you can see, are totally identical to the previous one we saw. So to the while loop example we saw on the previous slides. But of course it's much more compact. Okay, any question about what we saw until now? Okay, I have a question for you. So what if I remove from the second line of this piece of code the escape sequence \n? What's the result of removing that escape sequence?
Everything on the same line.
Pardon?
You print here j is equal to 0, here j is equal to 1, etc. on the same line.
Yeah, that's true. So the result is printing everything on the same line with no space in the middle of the value of I and the successes here. Okay? So the first printing is on a line, the second printing goes exactly on the same line, but you don't end up having any space between the last digit of the first print and the first character of the second print. Okay? Yeah. That's it. So, okay, so now we are able to perform many times the same task by using the while loop and the for loop and the blocks. What about, is this enough to write any possible program? Not really. And to do it, we also need the condition the conditional statement if then. So the idea is that we want to execute a piece of code included into a block if and only if a Boolean condition holds. So if the Boolean condition is true, then execute the block. Otherwise, does not execute it. Do not execute it. We have an extension for it. We have also the if then else conditional statement, which basically do what you may imagine. So the idea is that I have a block, I have a condition and two blocks. And if the condition holds, then I will execute the first block, otherwise I will execute the second one. Easy. Okay, can we have... Okay, any question about what we saw? Probably you already know all this stuff. Yeah, please.
Do we have else if in C?
Pardon?
Do we have else if in C? The condition else if, so we can have another condition.
Yeah. So your question is, can I write? Well, not really. No. Okay, let me repeat your question and then answer in a proper way. Do we have, can we, in some sense, shortcut an if inside an else by writing else if instead of having to place the if inside the else?
Yes, because some languages allow...
Okay, no, in the standard C it's not possible to do it. Okay, so in the standard C, these are all the statements you can use.
So if I wanted to add another condition, I would have to do if
A
is equal to 2.
Yeah, you have to embed the other condition inside one or two blocks.
Okay. So it would be else if.
Yeah. Okay. So probably I missed to stress one particular thing. A block of instruction is something contained between two braces or a single instruction. So for instance, I can write something like, let me go back to the previous slide. So in this previous slide, we have a block of instruction between braces in which we have one single instruction. Okay. Well, since the block consists in one single instruction, we can remove the braces. Okay. So one single instruction is actually a block of instruction. And from the functional point of view, is exactly the same. But my suggestion is to always use the braces, because you may end up in a tough to understand situation in which, for some reason, you decide to avoid to use the brace, and because of the indentation, you think of many instructions are performed into a block, and this is not the case. Oh, by the way, let me say something about the indentation, which I missed to say. So once you enter into a block, is a good practice to start writing your instruction a little bit on the right. So to have a visual representation of all the instructions included in a single block. And this is quite useful, especially for the while loop and the while loop, for loop, and if statement, because you can simply by looking at your code skip all the block if you want to go through the code and say, okay, this part I know that all this instruction belongs to the same if, and you can do it quite easily. But actually, from the syntactic point of view, I mean, no matter where you place the instruction, it can be on the left, on the right, two instructions on the same line, of course, because we know that all the instructions end up with a semicolon. So the compiler is able to understand also messy code, let's say, but I mean, it's a good practice to use indentation. So to place, every time you open a brace, to start writing your instruction a little bit on the left, on the right, sorry. And as soon as you close your brace, again, go back to the previous with previous indentation. Okay, concerning indentation, is also important to notice that if you are coming from Python, in Python indentation are part of the syntax. So in Python, blocks are defined by indentation. Okay, so all the instructions which are indented in the same way, such as subsequent instructions which are indented in the same way, belongs to the same block. As soon you start a different indentation, you end up in a different block. Okay? So in Python you don't have braces, just to simplify all this stuff. But this is not the case. So in the C programming language, braces are really important. You were asking a question.
About the semicolon.
Yeah.
If we have a sequence of instructions in between the braces, we have to run each line with a semicolon, or we don't have to put it at the end of the last brace.
Right. So let me repeat your question for the guys at home or YouTube. I mean, your colleague is arguing that while the instruction inside the block should be always ended by a semicolon, the block itself is not ended by a semicolon. Okay? So if you close the brace, you don't have to place a semicolon just after the brace close, and this is true. Okay? Any question? Any further question? Not really. Great. So let me show you some. Okay, let me show you some example. If you you can find them on YouTube, on Moodle, and wherever you want. So if you remember during the first lesson, I give you an URL which brings you to the Moodle of this course. On the Moodle of this course, you will find also the exercises I'm going to show you. And I kindly ask you to try to solve them. I know they are, I mean, pretty easy, but still I rather prefer that you try to solve them. Let me see whether I'm able to. Here we are. There we are. Not really. So let me try another way. This way. Okay. So we want, these are some very simple exercises just to try to see whether we understood all the syntax until now. So for instance, write a program to both compute and print the sum of 10 and 13. So let's try to do it all together, if you don't mind. Well, to do it, let me open a terminal. Yeah. Well, let me first of all try to do a different thing. This is my example, and let me open file, let me call it x3. I mean, I'm using a quite standard text editor, but you may use any text editor you prefer. For instance, you may use a Visual Studio so the program we saw during the installation of Ubuntu, and sometimes I demo the installation of software by using the graphical user interface. We saw how to install it. But I mean, it's not really important at this point because we are going to write quite simple, easy programs, and so I don't want to bother you with all the details. Let me see. So we want to write program to both compute and print the sum of 10 and 13. So this is my text editor. As I told you, you can run it by executing this command gedit space x3.c, meaning I want to edit this file, so a file named in that way. I mean, this is a new file, and we hadn't any file of this kind inside my directory, and here you can see the directory in which I'm placing this file. Of course, this is my personal directory. You will end up with a different directory. For instance, probably tilde. Okay, so let's write the program to perform what we did. First of all, we have to write the template we saw during the last lesson. The template was something like include argc argv return 0. This was our template, if you remember. So how can I compute the sum of 10 and 13 and then print the output? Well, for instance, I can have two different variables, just to I13 and let me write in this way, j. Well, we already saw the shortcut, so let me write the shortcut, j equal to 10. So by issuing this instruction, I'm basically declaring two variables and assign them to 13 and 10 respectively. The two variables are I and j. Then I can, of course, print f, and let me write print f of what? Of a string whose content would be the content of the first variable plus the content of the second variable equal to the sum of the two. And to do it, I must use the percentage placeholder d. So percentage d again equal to percentage d. So here I'm saying I want to print in the standard output 3 values computed by our program. And in between of the first two will be there will be a plus, in between of the last two will be an equal. Then I close my string, and then I write I, j, meaning the first value I want to represent would be the content of I, the second value I want to represent is the content of j, and then j plus I, or I plus j, I mean, it's the same. So as you can see here, the last, let me use a word that still hasn't been introduced. The last parameter here is an expression. It's not a variable, an expression. And then save it. So to save it, you can press this button. Here I'm again, since I in my system I have in my system the program is in my system is set up as an Italian system. You can see salva, otherwise it would be save. And by squeezing it, I end up in having saved everything. So now let me go to the terminal. So now, since I'm executing the gedit program, I'm stuck in some sense with the terminal. Because as you may remember, the terminal provides you a prompt as soon as the program you have is executed ended. However, our program, which is gedit, is still there. So either I close it, or I press Ctrl Z. Ctrl Z. By pressing Ctrl Z, I'm basically suspending, in some sense, the execution of the program. Okay? So the program is not more working at this point. I can see the window, but as you can see, I'm not able to change anymore the content of our file. Here I'm getting an error message because I cannot the program is not responding anymore. So I can try to place the program in background, and to do it I can simply issue the command background. Okay. Now by issuing the command background, the command background, I'm basically saying the last program which was stopped should be run as a program in background, and I should be able to issue other command on the command line. And this is why now this program is working, and I got my prompt on the command line. Is it clear? So the idea is, I was running a program. Since I was running a program from the command line, I wasn't getting any prompt from the command line, so I wasn't able to execute another command on the command line. So to go back to a standard situation in which I'm able to execute a command on the standard line, first of all I need to stop the execution of the previous program, and to do it I press Ctrl Z. By pressing Ctrl Z, I'm basically placing my gedit program on hold. And so I go back, I got back my prompt. So by issuing the command bg, which means background, I'm able to put my gedit program on background. So now the gedit program is working, but I'm able to use the command line again. So the command line is now more reserved in some sense by the execution of gedit program. Is it clear? The very same thing, so let me close the gedit program here. The very same thing can be done from the very beginning, could be done from the very beginning by using the ampersand symbol, which is a very special symbol for a command line. So the ampersand symbol means, look, I want to execute the program gedit, or better, I want to execute the previous command, but I want back my prompt. So the program in some sense is placed in background. And by issuing this command, I'm getting my prompt immediately back. Okay? So now here we are. Let me go back to the C programming language. So if I look inside my directory, I can see the program I just wrote, just written. Now, this program, well, the source code that's just written. So now I have to compile it to execute the code of this program. How can I compile it? To compile it, I can use the GCC compiler, and we can do it by writing GCC x3.c. So let's try to do it. Oh, we end up with an error. And this error is, highly described in some sense, because the compiler understands what's going on into our program, and is telling us that probably we are missing a semicolon. And this is exactly the same. This is exactly what happens here. So here we wrote an instruction, but we missed to end up the instruction by writing the semicolon. So let me add the semicolon here and save the program, and let's try to compile it again. Here we are. So by issuing GCC and the name of the source code, we end up in executing the GCC, no error message on the standard output, so we may assume that everything went as we expected. If we try to see inside the directory, the current directory, we end up in understanding that the GCC program produce a file named a.out, which is the executable program. So that program can be executed. So how can I execute it? We understood that to execute a command in the shell, we have to write the name of the command we want to execute. So we want to execute the program a.out. So we may try to execute it by writing the name of the program we want to execute and pressing enter. And the result is an error. Why? Well, the message is in Italian again, but is basically stating that the program a.out hasn't been found inside our system. How it is possible? I mean, we saw it on the current directory. Why is the system not executing it? Well, by default, the system does not admit to execute a command without providing a full path to it. And by full path, I don't mean an absolute path, but any possible path. So if you try to execute a command and the command is not on the standard path, let's say, the program is not found by the system. So we have to specify a path to the program, and a path to the program could be, for instance, the current directory. / is the current directory, a.out, a.out. If I try to execute it, I end up in this, which is a mess. Well, I mean, the result is correct, but I mean, I was expecting to go to the next line. So I was expecting my standard output on one single line and then the prompt to the next one. But the point is that we haven't set to the printf command to go to the next line just after printing our string. Okay, and that's why our prompt is exactly on the same line on the start of our standard output. Is it clear? So how can we tell our program that we want to go to the next line? Well, by using the escape sequence \n. Again, I'm adding the \n sequence to I'm adding the \n sequence to my string. I'm saving my program. I try to compile it again. I try to execute it. No error. I try to execute it, and that ends up exactly what we want. Okay? Now, is it really mandatory to get always the same name for the executable? So is it possible to get from the compiler directly a new an executable having a different name? I mean, of course, once you have compiled your source code, you may change the name of the executable simply by moving it to a different file. But can we, in some sense, ask the compiler to provide a different name for the executable? Well, yes. So let me remove the old file, and this can be done simply by using the -o parameter. So let me go here and let me write -o and I don't know, executable 3. Okay, so by issuing this command, I'll say I want to compile the source code contained by the file x3.c, and the result of the compilation should be placed into a file whose name should be x3. Okay, let's try to do it. Again, everything went as expected, and here we have the executable file named x3. Simple, clear. So why is it really useful, this kind of stuff? Why can't we simply use a program to do all this stuff for us? Well, the point is that probably during all of your program, you will be required to perform all this operation on servers, so on clusters, on big machines. So it may be the case you don't have direct access to these machines, but you have to work from home. And it's quite common to, since you don't know which functions are provided by remote systems, it's quite common to compile your own program on the remote system themselves. So this command, this instruction, these commands will be, I mean, quite useful in that case. And that's why I'm not using a standard interface to compile the program, which by the way are way more easy to use rather than doing the command line in this specific case. Okay, so let's see another program and then let's have a break. So let me go to here. So let me take, for instance, exercise number 4. Write a program to both compute and print the squares of all the natural numbers smaller than 10,000. Okay? So let's see. How can we do it? Let me, let me close this stuff. Let me rename it. So this was exercise number 1. Okay. Move exercise 3 into exercise 3. 1. Okay. And now let me try to solve exercise number 4. Again, I need to write my template. This is template. And so here we need to compute and print into the standard output all the squares of all the natural numbers smaller than 10,000. So we are repeating all the same stuff for a bunch of subsequent numbers. So we may use the for loop statement to solve it. So we will keep repeating the same block of instruction meant to compute the square root, sorry, not the square root, but the square of a value and to print it. Okay? So let's assume to have a block which performs that operation. We may able to keep repeating that block by using a for loop. So let me first of all write for int I equal to 0, I smaller than 10,000, for instance, I plus plus. So by using the for loop, I'm saying I want to keep repeating the following loop for all the values from 0 up to 9,099, 999. Okay, so now I need the block of instruction to compute the square of every possible value. So the value I want to compute the square will be the one contained in I, in the variable I. Okay? So to compute the square of a value, I simply need to perform I multiply I. So this is the only thing I need to compute the square of square value of the value contained in I. So I can directly compute the value and print it into the standard output by using the printf instruction. Well, I keep using the word instruction for printf. It's not really an instruction, but you will see why by the end of the lesson. So the idea is to printf d on the power 2 equal d and this is it. So the only instruction inside the block is basically printing in standard output the content of I hat 2 equal to another value which is evaluated as I multiply I. So it's quite easy, isn't it? Is it easy, right? No, not really surprising code. Let's try to compile it. Oh, again, I missed to send in background my gedit. To compile it, we may use gcc x34c and x34. no complaint from the compiler. So if I'm looking to the correct directory, I end up in noticing that my program has been compiled and placed into a file whose name is the one I provided, so x3_4. If I try to execute it, and again I must provide a path to execute it, a full path, which I mean doesn't really mean you have to provide an absolute path. It could be a relative path, but for sure it should be a path. And by executing the code in this way, I end up with this stuff. So easy. Of course, as we saw the last time, I can redirect the output of my program to a file by using the shell. So how can I fill a file by the output of my program? Well, I can simply write greater than and the name of the file, output for instance. The execution ends up with no error. If I use less to interactively see the content of the file, I end up with the result of the execution. Any question? This is simple. Let me see if you are still there. Can you see all this stuff from home? You on YouTube? I hope so. Sorry, what's your name? Marco. So you are coming from Fortran, right? So it seems probably it's much easier than Fortran, this as far as the syntax may concern.
Yes, now
Sì, lo so, grazie.
Sono ancora ancorata alla WS.
È stata addolorata?
Sono ancora ancorata alla WS.
Ah, sì, però il problema è quello lì, che lei mi domanda delle cose e io non so cosa risponderle. Se io dovessi rispondere a tutti quanti su, come dire, su tutti i sistemi operativi, su tutte le interfacce grafiche che usano tutti quanti, io non saprei più da che parte pigliare.
No,
vede, cambiano una versione, siccome io non uso quello nello specifico.
No, posso immaginare una strada, perché pensavo che Visual Studio magari si comportasse in maniera abbastanza...
Guardi, io le mostro come viene a me.
Ubuntu è
No.
Me lo sono fatta la macchina virtuale, solo che devo installare un po' di cose, quindi era un po' pigra. Ho detto che per oggi andava bene Windows.
Cioè a me viene fuori così.
Ah sì?
Questo è quello che vedo io. Installato da repository Microsoft.
Ma c'è anche un compilatore il Visual Studio, no?
E no, utilizza
no?
allora, di solito tende a
beh.
scaricarsi dei plugin, cioè, mettiamola così, se io comincio a scrivere un programma in C, lui si accorge che sto scrivendo un programma in C e mi suggerisce di installare un plugin che contiene il compilatore per compilare quel programma.
Ah, ok. No, su Windows me lo chiedeva all'inizio che cosa volevo installare, ho installato un po' di cose
Poi,
semplici.
per esempio io adesso in questo momento qui sto scrivendo i lucidi, cioè sto
ok.
modificando i lucidi.
Sì, sì.
E quindi ha tutta una serie di plugin che lei può utilizzare per quello che le pare. Adesso qua, vabbè, questi sono gli esercizi, no? Io posso cambiare qualcosa, adesso cambio quello, lo ricompilo e
È una sorta di tech maker ma per tutto praticamente.
Sì, cioè il bello dello studio è che in realtà lei ha un sacco di plugin. Io per esempio per fare quello che mi dice lei vado su Preferences,
Che io non ho, il mistero del
vede,
perché non
sarà
ce
quello,
l'ho.
Settings,
Ok.
e lui mi mostra tutte queste cose qui.
No, va bene, allora me lo installo
E poi,
su Windows,
vede, per
su Ubuntu.
estensioni, guarda c'è un'estensione C++ qua, allora lui mi domanda come vuoi che si autocompleti, cosa devo fare, qual è il compilatore, vede?
No, io ho un sacco di altre cose, ma questo qua non mi appare quando vado su.
Perché
Perfetto.
cioè io non,
No,
per
no,
quello,
posso-
non, per
pensavo
quello
li facessi
allora è uno
uguali.
strumento utilissimo, però io tendo a non usarlo a lezione perché poi va a finire che uno lo usa da una parte, uno lo usa dall'altra, mi fuori un disastro. Già mi sembra che questo concorso contenga troppe cose, ci mettiamo a insegnare anche le interfacce grafiche.
No, no, ma capisco esattamente il problema, non si preoccupi.
Mi spiace non poterla essere d'aiuto,
No,
però
ma
veramente.
che pensavo soltanto che semplicemente il gesto fosse uguale da un
In teoria sì, invece no.
Ma
Installato dai repository Microsoft, quindi non ti posso dire. Sarà una versione. Poi lo tiene anche aggiornato, quindi non capisco molto, non dovrebbe essere neanche una versione vecchia.
volete andare avanti con guai terminati.
Servizio
Perché
usario,
me-
guarda, io lo uso con molta soddisfazione, guarda. Oppure usi Edit,
No.
in Edit qualsiasi va benissimo.
No,
Guarda.
posso sempre fare tutto in guai.
Allora meglio pure. Ok, allora. Ok.
So let's go back to the lesson. Okay? So right now we are able to write programs in a very naive way, in a sense. So we are aware of basic syntax. However, I mean, as you will see, writing programs with all the stuff, especially the stuff we see until now, is not really easy. And we will see why. Easy and efficient. And we need something more. To explain why what we saw until now is not sufficient, let me go through this basic example. So, let's assume we want to compute the factorial of a bunch of numbers. So the factorial is basically a function aimed to multiply all the natural numbers smaller than a given number. So the factorial of 10 is 10 multiplied 9 multiplied 8 multiplied and so on and so forth until 1, because of course otherwise if you keep multiplying everything until 0, you end up in 0 all the times. So computing the factorial of a number is quite easy by using what we saw till now, because we can simply use a for loop. And for instance, the factorial of number 10 can be obtained by assigning a variable named fact, as you can see on the slide, the value 1, and then for all the value going from 1 up to the number we want to compute the factorial, in this specific case 10, we multiply fact by I. Okay? And this ends up in the factorial of the value 10. So if you want to compute the factorial of a absolute number, we basically have to keep repeating this block of instruction for all the number we want to compute the factorial. So this piece of code can be copied and pasted exactly in the same. To compute the factorial of 7, we only have to change the condition of the for loop, turning it from I less or equal than 10 into I less or equal than 7. And that's enough to compute the factorial of 7. Okay? Now, while the previous code is correct from a functional point of view, so it produces exactly what we aim, there are some issues in the previous code. The first one is the complexity. Why is complex? Because I mean, every time you want to compute the factorial for a new number, you have to copy a bunch of lines of code and then paste them and then search into the line the precise position in which you want to insert the correct number. Okay? So, as an example, in the example of the previous line, if you want to compute the factorial, you know how to compute the factorial of 10. If you want to compute the factorial of 7, you have to copy 5 lines and replace 10 by 7. But I mean, doing all this stuff is not really easy, in some sense. Moreover, there is a kind of explosion in the number of line of codes. Why? Because every time you want to compute the factorial, you have to repeat all those lines that are used to compute. And for the factorial, it's not really a problem because they are 5. But let's try to imagine a tougher situation in which you want to compute a function which is really hard to be computed, and you need many more line of instruction, many more instructions to compute it, and every time you want to compute that function for a new value, you have to copy, I don't know, 1 billion line of code. So, the previous code is not really smart from the point of view of the number of line of code. And moreover, last but not least, is artifact fixing. So what if the very first time you wrote those lines which are meant to compute the factorial, you committed an error? And you basically copy and paste that lines many times in your code. So if you discover, at the end, you discover an error in the first 5 lines you wrote, you end up in having that error exactly the same error in all the lines you copy and paste. Okay? And so to fix it, you have to go through all your code to fix all the problem you may have caused by introducing that small error at the very beginning of your coding session. So from this point of view, the previous code is not really nice. It would be much better if we had chance of using a kind of module. Let's say it would be, so let's think a situation in which that 5 lines can be in some sense embedded into a coding module, giving you the chance to to use that module many times in an easy way. Okay? So, however, to perform this operation, we have to solve, we may use this technique also to solve some other issues. For instance, by using this kind of syntactic facility, we may split the original problem into sub-problems. We may need to do it. Okay? We may implement these sub-modules to solve all the original sub-problems and then combine all the results to get the final result. Okay, so going back to the example, let's assume we want to compute the factorial of 10, 7, and I don't know, 100. If we had the chance of using a kind of module to compute the factorial, we may simply focus on computing a general module to solve the factorial and then apply it to 10, 7, and 100. Now, what is really important about such kind of module is that they should be usable in an easy way. They should be reusable, meaning you wrote once, you should be able to use them many times, and moreover, they should be in some sense isolated from the rest of the world. So you should be able to focus exclusively on the problem without taking care of anything else outside the problem itself. Okay, so from the point of view of the model, you shouldn't be caring the fact that the model itself is used to compute the factorial of 10, 7, and 100. You should focus on the fact that you want to compute the factorial of a number, of a general number. So no matter what the number it is, the number is, okay? So this is syntactically implemented in the C programming language by using functions. So functions are basically syntactic modules in our program, and they are implemented as blocks of instruction equipped with a name, some input parameters, and an output. So you have a block of code, you have these input parameters, so this value that you want to pass to your block of code, so to your function. You must provide an output, or better, a type of output, and a name for the function. And that's all. Okay. And the idea is that these modules are named function because they are meant to implement mathematical function, and that's why they are named functions. They are named functions. So let's see the syntax to define a function. The syntax to define a function in the C programming language is the one you can see on the slides. We have, first of all, we have to define what is called the signature of the function. So the signature of the function is the output type, the name of the function, and the name and the type of the parameters we want to pass to the function. Okay? And this is the function signature. Then, after the function signature, we have the block associated with that function, which is named function definition. So you are defining the function itself. And that block must contain a special instruction called return, whose goal is to return the control of the function and the value produced by the function itself. Okay? So easy. Let's see an example, and in particular, let's see an example of the factorial. So in this example, we are trying to compute the factorial function, to evaluate the factorial function. we have a function whose signature is unsigned int, the name of the function is fact, and this function takes one single parameter, whose type is unsigned int, and whose name is am. Okay, so my function is taking one single value. That value is placed into let's say, what is called formal parameter, so a kind of variable, if you want, whose scope is not necessary to be defined, but basically exists exclusively on the block, on the pollen block. And so this is the signature. Inside my block function definition, I'm declaring a new variable result. And since it is inside the block, of course, the variable itself exists exclusively inside the block itself. So once I'm outside the block, outside the function, the variable doesn't exist anymore. And as we did before, for all the value of I going from 1 up to n, which is the parameter, the formal parameter, keep repeating result by I. Okay? So in this way, I'm not saying I'm computing the factorial for the value 1, 2, 3, 100, or 10,000, or whatever. I'm computing the factorial for a generic number n. Once I've computed it, I must return as a result the content of the variable result, which is the factorial of the number I passed as a parameter. That's it. Okay. So this is a simple example of function. I mean, if you came from any other programming language, probably you already see it. So, what if a function does not provide any result? For instance, let's assume we want to write a function which simply prints something in the standard output, but does not produce any numeric result. So how can we implement it? We can implement it using a special data type, which is the void data type. The void data type is a type meant to say, look, I'm not going to return any value. Okay? So if you find a signature just like the one you saw here, you are seeing here, what I mean is that I'm doing something, so my function print even or odd, which takes one single parameter, do something but does not return anything. Okay? Is it clear? Okay. And so we don't need to provide any value to the return instruction. But actually, we don't even to provide a return instruction. So it's not needed. So the return instruction in this specific case simply means, look, I'm ending the execution of the function. Okay? Let's try to have a look to this piece of code. Here and try to understand what's going on here. So here I'm taking as a parameter a given value. That value will be placed into the formal parameter n. Then I'm testing that condition. That condition basically takes n divided by 2. Since both 2 and n are integer value, that division is the integer division. So for instance, if the value is odd, for instance 5, I'm getting 2. So I'm not getting the algebraic result of dividing by 2 a number, I'm getting the integer result, the integer part of the division. So once I take that value and multiply by 2, I end up with a result which may or may not be equal to n. If the result is equal to n, this means that the division by 2 ends up in a value which multiplied by 2 is equal to n, and this occurs if and only if n is even. Okay? So if, for instance, let's assume n is equal to 5. 5 divided by 2 is 2. 2 multiplied by 2 is 4, which is different from 5. And actually 5 is odd. What if the number is even? So let's take 6 for instance. 6 divided by 2 is 3, multiplied by 2 is again 6. So this condition was exclusively if n is even. So if this is the case, we print in the standard output even, and we execute the return instruction. The return instruction in this specific case is not meant to return a value, but is meant to end the execution of the program. Well, not of the program, but of the function. So it's a way to say, look, once you reach this instruction, stop the execution. You don't have to execute anything more. Okay? So from a functional point of view, it's more like, more or less like if I added an else just after the brace closed, and I included this odd into the block of the output. Of course, if this condition does not hold, the return will be not executed. Why? Because all the block wouldn't be executed, and in that case we will print. Well, the program would print odd, and since the block of the function ends there, the execution of the function will end. Okay. Here you can see that the return instruction can be used to end the execution of a function, but it is not mandatory in this specific case. While it's mandatory if the output, the return times is different from void. So if your function is meant to return an integer value, you cannot conclude the execution of a function without returning anything. You are forced by the compiler to return something. Is it clear? Okay. So, finally, we may have a look at our God provided template. So if you remember in our template, in the template for our program, we had something like int main, open parentheses, int argc, yes, char star argv, close parentheses, and then brace, open brace, and then our code, and then close brace. Oh, so now we understood what was that part of the code. That part of the code refers to a function, and in particular, the main function of our program. Okay, so the main function of our program is the how can I say, the function which will be executed once we try to execute our program. So every program in C must contain the main function, and all the other functions will be called by the main program. Now, what are the parameters that I'm passing here? And why the return type is int? So let's focus first of all on the return type. Well, in POSIX, programs must always return an error code. So, in particular, 0 means success. So that's why in our template, if you remember, the last line of the template was just before the end of the blocks was return 0. Okay? I mean, it's not really mandatory because if you don't write return 0, the compiler usually adds by its own. But I mean, to be clear, I mean, to be formally correct, it's much better to write it. So if your program has a sex, the program must return 0. Otherwise, there is a set of code depending on the result of the program, which for some reason might end up because I don't know, wasn't able to allocate enough memory to complete its task, or it wasn't able to load the file, or I mean, you are trying to compute the square root of a negative number or whatever you want. Okay? So the return code really depends on whether your program has success or less, or not. As far as the parameters may concern, the first parameter in the main function is the number of parameters in the execution command. So once you have compiled your program, since your program ends up to be executable as a standard command in the command line, you may provide to your program also some parameters, or better, you may provide to the execution of your program some parameters, such as the one you can see on the slide. So if I've compiled a program and the program name is a.out, and I try to execute it by passing as parameter a, 12, and 3, then the argc parameter assume value 4. Why 4? Because in the command line we have 4 distinct string words. The first one is the name of the function the name of the program we are executing. The second one is a, the third one is 12, and the fourth one is 3. Okay? Again, the first parameter in the main function is the number of parameter plus 1 in the execution command. Clear? Okay. Now, we understood how to define a function. We need a signature, we need to define a function by using a block, but how to use them? Once I have defined a function, how can I use it to compute the factorial of a specific number? Okay? So my goal is once I have defined a function, I declare the function, is to use it to compute the factorial for a specific number I have in mind. For instance, the factorial of 10, the factorial of 7, and so on and so forth. How can we execute? Okay. How can we execute a function for a specific parameter, value for a parameter? Oh. We can do it by using following syntax. So to call the function, we can write the function name, open parentheses, the value we want to assume the parameter, close parentheses. So the value that we want that the formal parameter assume, that we want to assign to the formal parameter, is called actual parameter. So while the formal parameter is more or less, I mean, it's not really, but it seems to be a variable, behaves like a variable. This actual parameter should be an expression. Okay, so it should be more or less like what we may see on the right of an assignment. Okay, so the formal parameter is what we are used to find on the left of an assignment, the actual parameter is what we are used to find on the right of an assignment. Let's try to okay. So once we call the function in this way, we are basically asking the function to compute a value, which is the return type. That value can be used inside any expression we are written. Okay. So let's have an example. For instance, we have already written the function factorial, already defined, and I recall you that the factorial function has name fact, return an integer value, and takes as formal parameter again unsigned integer value. So by using that function, we may compute all the factorial, so the factorial for all the value from 3 up to 500,000, as in this code. And this is quite simple. So we have a for loop, which starts from 3 and goes up to 500,000. K starts from 3 and goes up to 300,000. And we can compute the factorial for a generic number in this range by applying the function, by calling the function factorial. The result of the function factorial is then assigned to a variable whose name is k. So again, so here we are doing some nasty thing. Okay. So we are computing the factorial of k, reassigning k by that factorial, that we are keeping repeating all this operation until we end up with a value which is larger than 500,000. Okay. Any question? So here we are not computing the factorial for all the values from 3 up to 300,000. We have basically computed the factorial for 3, then computed the factorial of 3, and so on and so forward, until we end up with a number which is larger than 500,000. Quite easy. Again, if you come from a different programming language, probably you already know how to do it. So going back to the original example, which was the one in which we were trying to compute the factorial of 10 and factorial of 7. Once we have defined the factorial as we already did, the code becomes this one. So really easy to read. Much more readable. What if we introduce an error inside the computation of the factorial? Well, in that case, really easy to understand what's going on, but not really easy to understand what's going on. But once we discover the error and we understand the error is on the factorial function, we don't need to change anything here. We can focus on the factorial function. And if we change the factorial function, then automatically change in every code. Okay? Easy. Now, do we always need to define a function before calling it? No, it's not really needed. So the really important thing is that you have a signature of the function before the call. So as you can see here, we are using the function test before defining it. And this can be done simply because we have specified the signature of the function. Once you have specified the signature of the function, you can use the function test. This is extremely important for what we will see later on. Probably on Monday. Now, this is quite nice, but some other questions may arise. So, for instance, let's again take into account the function factorial. do we always need, let's assume we keep writing something that need the factorial function. For some reason, our programs always need the execution of the factorial function. Should we always start from the scratch? So should we really need to rewrite every time we write a new program the factorial function? No, of course. I mean, that would be a totally waste of time. Once we have written the factorial once, we would like to use this very same function many times, without the need of copying the function inside the code we are writing right now. And to do it, so to avoid to copy all the functions we already written, libraries, what is called libraries, are introduced. So libraries are a set of functions which can be linked to the program you are writing. And the idea is to have the chance of using library already written by you or by any other guys in your program. Okay, and so there are two kinds of libraries in general. One kind is called static library, and the idea is to embed all the library inside your executable. So all the binary code required to execute the program will be inserted into your binary code. And the second kind of library is the dynamic library. So a dynamic library is a library which is loaded at execution time. So in some sense you are saying to your program, once you compile it, once you are linking your program to the library, you are saying, look, I'm interested in using this function which is present in this library, but please load it the binary code at the execution time. So every time you execute that code, automatically the system loads the library and they execute the function you want to use. So the advantage of the first linking kind, let's say, is that for sure you can take your executable and move to any kind of system having the same architecture, of course, because your executable does not depend on any library on the system itself, because you embedded all the code inside one single executable. However, this end up in being a kind of waste of space, because every single executable which implement a specific function, which use a specific function, should include that function in the executable itself. So if you have, I don't know, 10,000 programs which require the evaluation of the factorial function, 10,000 programs will include the binary code to compute it. And this is a waste of time, of space. So, so from this point of view, the dynamic library is much better because in your system you will have one single file containing the code of the factorial function, and all the binary requiring the computation of it will dynamically load the code from the library itself. Okay, so the idea is to produce an executable from the source. You are basically performing two kinds of operations. The first one is the compilation of the source. So you are taking the source, you are transforming in binary code. Okay? And the second one is the linking of your code. The linking takes your binary code and the library to which is related, and produce the executable. Okay? Now, these two steps are actually executed at the very same time when you call the GCC compiler. So the GCC command automatically calls both the compiler and the linker. Now, how can we build a dynamic library in GCC? What dynamic library? Well, nowadays, almost everyone uses dynamic library and not the static one. So that's why I focus on the dynamic library. Well, to produce the dynamic library, you have to produce, first of all, two files. The first one is the file containing the signature and definition of your function, and will be named some name.c. And the second one will contain exclusively the signature of the functions. Why? Well, we saw that to use a function, to call a function, we need to provide a signature of that function before using it. Okay? So, if we want to define a library, we need to provide all that signature before calling the library itself. Otherwise, the compiler will complain, saying, I don't know what are you doing, what you are doing. Okay? And so that's why we need, first of all, to split the library, the definition of the function we want to include in the library into two files. The first one will include all the functions, including the signature. The second one will include exclusively the signature. The signature of the function we want to include. Once we have performed this operation, by issuing this command, we are basically producing the dynamic library. This command is the GCC command, so the one we use until now to compile our code. But we also need to provide two different parameters, at least two new parameters. The first one is minus fpeak, which is a parameter meant to say, look, I'm not really interested in the position of the memory in which the code will be executed. It's quite technical. But since there might be cases in which it's really important to know that you are at the beginning of the memory. For instance, let's imagine a situation in which you are dealing with an embedded system and you are trying to write the operating system of the embedded system. Okay. Now, how can we call a function inside our library? As already said, to call the function inside the library, we need to declare the signature. But since we already include all the signature inside our library, since we include all the signature inside our library into a file whose extension is h, we may simply tell to our compiler, look, the signature of the function I want to use are included in that file. And how can we do it? We can do it by using something called preprocessor. So the file .h is what is called usually header file, and that's why the extension. And to tell our procedure that we want to load that file before compiling the code, we may use what is called preprocessor. So the idea is that actually to compile a program we have to go through a process which first of all call the preprocessor on the source file, produce some result, then there will be a compiler, then the linker. So what is meant for the preprocessor? Well, the preprocessor can include external file in the source code, the source code file of your program, define and undefine macros, and evaluate macros. So every preprocessor directive begins with an hash. If you go back to our template, our provided template, the very first line of our template was hash include and something else. That is a preprocessor directive which is meant to include a file inside our source code. And in particular, that directive tells the preprocessor to include the file stdio.h taken from the, let's say, standard path. Okay? So, for instance, this is a directive for the preprocessor, this is a directive for the preprocessor, and so on and so forth. So what's the meaning of this directive? Define a macro. What is a macro? Is a, let's say, shortcut for something. In this particular case, we are defining the minimum, a macro, which is meant to evaluate the minimum among two values. So instead of writing this stuff, which by the way is test whether this condition is true, if it is true, execute the, return this value, otherwise return this value. Okay? So instead of writing this stuff on our code, we are writing simply min x, y. So to compute the minimum among 5 and 10, we can write min 5, 10. That's it. And the preprocessor takes care of substituting that min into the correct value. Okay? What about this instruction? Well, this instruction is a conditional instruction which tests whether min is true, and if is which tests whether if is has been already defined. If this is the case, then execute everything until end if. Or better, try to execute everything until end if. So in this specific case, test whether min, the macro min has been defined, and this is the case. So execute the second last directive, which basically undefine the min standard charter function, and then ends the if block in the preprocessor. Okay? So, in our template we saw, in our template program we saw preprocessor directives, we saw function definition, we saw types, we saw many things, and that's why at the very beginning I told you, please trust me and use this as a template. Because to understand everything, we need 2 lessons at least. Okay? But now, right now, apart from the second parameter of the main function, we understood almost everything. Almost. Okay? Any question? Okay, so my idea is to conclude the lesson here. On Monday, we will try to demo what we saw until now. So we will write a simple function to compute the factorial, as the one we already saw, and we will deliver a library which will include exclusively that function, and we will try to use it in a standard program. Okay? So Is there any question? Yeah, please.
Can we just create a function named min and do that operation?
Oh, thank you for the question. So your colleague is asking whether why are we required to define a macro and we can simply use a function to compute the minimum? Well, the point is that a function is evaluated at execution time, while the macro can be evaluated at compilation time. So for instance, well, it really depends on the parameter, of course, but let's assume we want to compute the minimum among 5 and 10. This, of course, can be evaluated as at execution time, at compilation time. So by using the macro function, I'm saying, look, I want to know it right now. So at compilation time. While in the case of the function, depending on the parameter you provided to the compiler, it might be the case that the function is evaluated as execution time. Okay. So by computing a function which computes the minimum, by evaluating a function which computes the minimum among 5 and 10, if you don't tell the compiler, please try to evaluate as much as you can right now, that function evaluation will be executed, but will be done at execution time. Moreover, okay, this is more or less the big difference. Okay, let me make an example to clarify also this stuff. Let's assume that for some reason you are writing a piece of code which depends on the version of the Linux system you are using. So if you are using a version of kernel which is less than 5.6, for instance, you have a piece of code. Otherwise, you need to compile a different piece of code. Okay? So in that case, the selection of which piece of code to execute can be done at compilation time. Okay. Okay. So in that case, it makes sense to have the selection done by using the preprocessor. So before the compilation, you are basically selecting which branch of the code you want to execute.
We can, that function is type dependent, or I can provide x through float numbers or through int numbers, and the function will perform good.
No. So the macro are usually solved at compilation time. So does not impact. Well, I mean, you improve the execution time because all the evaluation are done by the preprocessor usually. While if you use a function, the execution will be postponed to the execution time. Okay.
But I use all kinds of like error handling, or for example, if someone puts a float, no, not a float, a char instead of a number.
I see. Yeah, well, the preprocessor there is a kind of, there is an error handling done by the preprocessor, of course. So if you try to provide something which is not, understandable for the preprocessor tell you, look, you are doing something wrong. Or, for instance, if you use an if-def statement, an if-def statement, and you don't close it, the preprocessor tells you, look, you are doing something nasty. the preprocessor is also quite useful because it may be the case that for some reason you may want to use, well, okay, don't worry, you will see. Okay, if there isn't any other question, I mean, this stuff, of course, is far away from what would you do in Python, for instance. Yeah, something similar is done in Fortran, if I can remember well. But probably you haven't seen it, okay. Let me think. Well, I mean, it doesn't make much sense you having a preprocessor on an interpreted programming language, just like Python or you know, Julia or whatever, because of course the compilation and the execution phase match in interpreted programming languages, and so the preprocessor basically and the compiler are executed exactly on the same, but not exactly, but just one just after the other. So, and on the very same system. While in the case of a compiled programming language, the preprocessor is executed at compilation time, while the functions are meant to be executed at the execution time. So it may be the case that you compile your program on one system and you execute it on a different system. So that's a really important difference. Okay, so see you on Monday then. This is all. Thank you for the attention and have a nice weekend.